Hi, my name is Bob Hanlon, here to talk to you today about Rudolf Clausius and his undaunted journey along the road to entropy. Just as a brief review, and today I'm going to use a nice map to show you where these scientists worked. The work of Thomas Newcomen and James Watt occurred in the early 1700s, mid-1700s up in Glasgow. And then this was followed by the work of the development of the high-pressure steam engine down in Cornwall, around 1800 or so. Following that, Sadi Carnot in Paris did the first theoretical analysis of these high-pressure steam engines. And finally, James Joule did his work of work-heat equivalence back in 1847 in Manchester. Today I want to talk with you about Rudolf Clausius, who came up with the first law of thermodynamics. He did his work in Berlin. I want to talk with you about his analysis that was done in 1850. So just as a review, I want to talk with you about Sadi Carnot and his work of 1824, which was a masterpiece that contained a single flaw. He looked at a steam engine and said heat was coming in at a high temperature, heat was exiting at a low temperature, and work was generated. In his analysis, he said heat is conserved. The heat in is equal to the heat out. He also assumed work happens mysteriously when caloric fell from a high temperature to a low temperature. 1847, James Joule came along and said, no, heat is consumed in an engine, and the difference between the heat in and the heat out is equal to the work generated. This was all based on his very simple but very definitive experiment showing the consequences of a drop weight, a spinning paddle, and warming of water. I covered that last time. Rudolf Clausius then came along in 1850 and did a great job in developing the first law of thermodynamics, and I want to use some of his direct quotes. Someone once said it's best to use direct quotes to reflect what a scientist was thinking, so that's what I want to walk through here. Clausius said, Carnot showed that whenever work is done by heat, a certain quantity of heat passes from a hotter to a colder body. You can see here the beginnings of the second law of thermodynamics, and entropy had not yet even entered this discussion. Then he said the careful investigations of Joule have almost certainly proved the law that the quantity of heat developed is proportional to the work expended. Furthermore, other facts have lately become known which support the view heat is not a substance. Here you can see Clausius putting the dagger through the heart of the caloric theory of heat. Then he said, if the above is so, it is admissible to state that heat may be transformed into work. This is, in essence, what James Joule demonstrated. Finally, he said, these facts almost compel us to accept the equivalence between heat and work, and that the accomplishment of work requires an actual consumption of heat. And it was with this that he went forth and did the analysis of Sadi Carnot's engine. He also referenced the work of William Thomson, who later became Lord Kelvin, and I quote again on his assessment of Thomson's work. William Thomson concludes that in the present state of the science, the principle adopted by Carnot is still to be taken as the most probable basis for an investigation of the motive power of heat. And then he said, again, further quoting Thomson, if we abandon this principle, meaning if we abandon the caloric theory of heat, we meet with innumerable other difficulties, an entire reconstruction of the theory of heat from its foundation. It was almost as if William Thomson was intimidated by this task in front of them. And you can see how deep the caloric paradigm was and how difficult it was to climb out of this deep valley. Rudolf Clausius, though, was undaunted. As he wrote, I believe that we should not be daunted by these difficulties. Sure enough, he wasn't. He went forth, took Sadi Carnot's work, and then applied James Joule's finding and used that as an analysis of the piston inside Carnot's heat cycle. In the piston, he showed that heat entering a system from a hot source, heating up a gas here, increasing the pressure, doing work here, he said that the gas inside that system has a property called U, which he called, later became known as the internal energy of body. And then he said that the change in that property U is governed by heat coming in minus the work coming out. If there was no heat and no work, there was no change in this property. And this became the beginning of the conservation of energy. So Clausius completed Carnot's work by eliminating the caloric theory and replacing it with the theory of energy and its conservation. So this was in 1850 again. It would take another 15 years for Clausius to come up with the concept of entropy. But in between 1850 and 1865, much work was going on in this whole field of thermodynamics. A lot of this effort was led by William Thomson. He, together with William Rankine, P.G. Tate, and even James Clerk Maxwell up in Glasgow, Scotland, they created the whole science of thermodynamics out of scratch. They pulled everything together, did a masterful job in bringing structure to the science. And in the process, Thomson and Clausius had many interactions around the concept of entropy. And actually, the concept of entropy rose from that back and forth work of Clausius and Thomson. I go into the details of all of this history, and it's a fascinating history, in my book, Block by Block, The Historical and Theoretical Foundations of Thermodynamics. Thank you very much for listening to this part of the story today. Look forward to seeing you next time. Goodbye.